Hello and welcome to another video in our basic geometry concept series. We are still dealing with the topic of triangles, and today I'm going to talk about the Apollonius theorem. Now, before even I get into the application of the theorem or what this theorem exactly states, let me start off by talking about the derivation of this theorem. Firstly, Apollonius theorem is associated with medians of a triangle. You can apply this theorem only if you have a median in a triangle. Without a median, you cannot apply this theorem. Now, what is a median? A median is that line segment which joins one vertex with the midpoint of the opposite side. For example, in this figure that I've drawn here, we have a triangle ABC, where P is the midpoint of the side BC. So AP becomes a median of this triangle because it is joining A with the midpoint of its opposite side. Now, to derive the Apollonius theorem, there are multiple different ways that we can do this in. One uses the Pythagoras theorem, which is a longer proof. One also uses vector algebra, which I'm not going to get into because it's not very important for aptitude-based examinations. I would rather use the cosine rule. And the derivation of cosine rule we have already discussed in a previous video. So if you want to go back and refresh your memory, you can go and watch that video as well. In this video, we're going to use the cosine rule to derive the Apollonius theorem. So to derive the Apollonius theorem, firstly, what I'm going to do is I'm going to consider this angle APB as theta, which means angle APC, I can say will be equal to 180 minus theta or pi minus theta. Whether you use degrees or radians actually does not matter. So keeping this in mind, first let me consider triangle ABP. In triangle ABP, if I apply the cosine rule, I'll get cos theta is equal to AP square plus BP square minus AB square by 2 into AP into BP. If I cross multiply the denominator to the other side, and if I take AB square to the left side and the cos theta term to the right side, then we'll get AB square is equal to AP square plus AB square minus 2 AP into BP cos theta. And if we do the same thing, in triangle APC or ACP, right? If you apply the cosine rule in triangle APC and perform the same operations as I have done for triangle ABP, then I'll get in triangle APC the fact that AC square is equal to AP square plus, I'm sorry, I think I made a mistake here. This should not have been AB square. I've taken AB square to the other side. It should be AP square plus BP square. So AP square plus CP square in the case of triangle APC minus 2 into AP into CP cos of 180 minus theta. Okay. I hope you can pardon my bad handwriting and hope you can understand what I've written here. Now what I'm going to do is I'm going to add these two equations. So let me demarcate where I'm going to write next. So I'm going to add equation 1 and equation 2. So I'm adding these two equations. I'll get AB square plus AC square is equal to AP square plus AP square. I'll still get 2 into AP square plus BP square plus CP square minus, I can take 2 into AP into BP and 2 into AP into CP common because BP and CP are equal. P being the midpoint of BC, BP and CP are equal. So I can simply take 2 into AP into BP common. And inside the brackets, I'll have cos theta plus cos of 180 minus theta. Now, if you remember your high school trigonometry, you will realize that cos of 180 minus theta is actually minus of cos theta. So this is minus of cos theta, this is cos theta, so both of these can get cancelled. So which means, simply put, I'll have the equation as AB square plus AC square is equal to 2 into AP square plus BP square plus CP square. Now, once again, BP and CP are equal. P being the midpoint of BC, BP and CP are equal, which means that BP square plus CP square can be written as 2 into BP square. So I can do one thing. I can represent BP square plus CP square as 2 into BP square, and I can take 2 common on the right hand side, and I'll get 2 into AP square plus BP square. This is what the Apollonius theorem states. That if I have a median in a triangle and the median is AP, then AB square plus AC square will be equal to 2 into AP square plus BP square. And of course, BP square can be either written as BP square or as CP square or half of BC, the whole square, because P is the midpoint of BC. This is what is the Apollonius theorem. Now, why is it important to know this theorem? See, Apollonius theorem is important to know and remember for the same reason that Pythagoras theorem is important to know and remember. In a lot of questions, wherever lengths of sides have been asked in about a triangle, if it's a right angle triangle, you can apply the Pythagoras theorem. In fact, the primary application of Pythagoras theorem in geometry-based questions in your aptitude-based examinations is to find lengths. If you want to find the length of a side of any geometric figure, look for a right angle, look for a right angle triangle, try to apply the Pythagoras theorem. It can actually lead you to the correct answer several times. Similarly, if you cannot apply the Pythagoras theorem, if there is no right angle triangle, but if you can spot a median in a triangle, immediately Apollonius theorem should strike you. We should remember that this is another theorem that can be used to find out lengths because it's an entire equation based on lengths of sides. It is as important as the Pythagoras theorem. Just like how we think of the Pythagoras theorem whenever there's a right angle in a triangle. Similarly, whenever there's a median in a triangle, the Apollonius theorem should pop up in my head as a possible option to figure out the length of a side that might be asked in a question. That's all for this video. Thank you.